Hey there, welcome to the effect size video. We're gonna slide our way in. First, I want to say that part of the reason this video is useful and that it exists and that I believe in the utility of effect size has to do with the fact that rejecting the null when you have a p less than 0.05 or less than your alpha level does not mean your hypothesis is correct. Means it's unlikely the data came from a random number generator. Is one different way to interpret that that we haven't mentioned yet in this class. There's a lot of space between a random number generator and your hypothesis, and so because this lesson is sort of repeated over and over in intro stats, most students come out kind of knowing it to some extent, but it's something that seems to be lost in psychologists over the years, so much so that some claim that it fades with additional training. And so I make it over and over, hoping that it'll be even stronger in you, so that when it starts to fade, it still maintains some presence in your mind. And I want to give you some alternatives to that method of analyzing your data because, as John Wickstead noted in a talk I quite liked at Psychonomics conference in 2019, science and psychological science maybe shouldn't be couched as a signal detection problem. And so to explain that, I'll first say that we seek P, but Wickstead argued that we should instead seek to accurately estimate the size of an effect, which is called D. We'll talk about Cohen's D in the course of this video. P is a low P and a P below a cutoff only really tells us whether there is an effect and doesn't directly tell us that either, by the way. But rather than trying to figure out whether there is an effect, why don't we try to figure out how large the effect is while realizing that 0 is a possible answer to that question? Because what null hypothesis significance testing allows us to do is make judgments about the likelihood that a difference between two means is due to chance, or essentially could have come out of a random number generator. Even though NHST is really widely used, we've discussed before that it's not without its problems. For one thing, the p-value you get out of a null hypothesis significance test and the number of people in your groups, so your n, turns out to be really closely related. That's true for two reasons. Number one, as the sample size increases, the standard error will decrease, which will in turn increase your observed statistical value. I'll talk in terms of an independent group's t-test here, so it'll increase your t observed. In addition to that, as sample size increases, your t-critical will decrease because you'll have more degrees of freedom. And so that combo of inflating your t observed and deflating your t-critical makes rejecting your null hypothesis more likely as your sample size increases. And on one hand, that makes total sense. As sample size increases, we should have more confidence in our data's representation of the population. It'll be less susceptible to outliers, variability, error, so it seems like a good thing, but can still result in problems. One specific difference, or one specific issue, is displayed in the table here. So each of these examples, 1, 2, 3, and 4 in the table, describe the same situation in that the mean of group 1 is 25 and its standard deviation is 5. The mean of group 2 is 22 and its standard deviation is also 5. So there is you're getting the same difference, the same size difference in each of these 4 examples. So you're essentially looking at the same effect, would be one way to think about that. So you see pretty quickly as you scan your way down that even though the size of the effect, the difference between the two means, doesn't change, the various measurements we take and the statistics we generate do. We've got different degrees of freedom. Though we have similar pooled standard deviations, we have different standard errors of the difference between the means because of this differences in sample size, which leads us to a different t observed and a different t critical. And you can see that even though, again, we're looking at the same difference between the means across all 4 of these examples, in the first 3, with ends of 6, 11, and 21 in each group respectively, we failed to reject the null hypothesis. But in the 4th example, when we've recruited 41 people into each group, so 82 in total, we have now a t observed that is larger than our t critical, and we do reject our null hypothesis and conclude that there is a difference between those 2 means. You can imagine taking it to the extreme. Take a huge sample of thousands of people, and you basically guarantee yourself a significant difference of some kind, no matter how small the actual difference was in practice. These means could be 25 and 24, but if you had 1,000 people in the sample, the difference would probably be significant. So what that means is, as sample size increases, we become unfortunately more likely to make type 1 errors. And so, to avoid that possibility, many recommend, and I recommend to you, that we use a measure that is not influenced in sample size in this way to add to our analyses. That's called effect size. The example is shown on here that across all 4 of these samples, effect size remains the same, is not influenced by the different sizes of those samples. Effect size is, at its most basic definition, a way of quantifying the size of the difference between 2 groups. And so by doing that, it allows us to move beyond the question of whether there is a difference between our groups, which is good because it's a pretty basic question, and actually allows us to ask, okay, how big is the difference? How well does my treatment work? Not does my treatment work, how well does my treatment work? How large is the difference between these 2 groups? So that makes it an important tool in reporting and interpreting effectiveness of manipulations, and is pretty rapidly becoming a standard in the field. In a lot of cases, journals will require that you report your null hypothesis results, but also an effect size of some kind. Let's think a little bit more about why we need these. So consider an experiment that Dosen conducted in the year 2000 to investigate the effect of time of day on learning. So the question was essentially, do children learn better in the morning or do they learn better in the afternoon? They recruited 38 children and randomly allocated half to listen to a story and answer questions about it at 9 a.m., the other half to do the exact same thing at 3 p.m. So their comprehension of the story was measured by number of questions answered correctly out of 20. So the kids in the morning answered on average 15.2 questions correct. Kids in the afternoon answered 17.9 correct on average, for a difference of 2.7. So great. Let's say you go through and do all this calculation. That's a significant difference. These groups are different. There is a difference between morning and afternoon. But the difference here is in almost 3 questions on this specific test. So what does that mean for the larger goal of figuring out whether children learn better in the morning or afternoon? Seems like the answer is afternoon a little bit, but how much better? Is that a meaningful amount? Or is it too small that we shouldn't worry about it? Or is it large enough that we should be hugely worried about it? We need to know how big the difference is, not just that there's a difference. The reason that we don't know how big a difference this is because I haven't told you anything about Dosen's test primarily. If you knew what was on it, you might have some idea of what a difference of 3 accurate answers might be, but I didn't, so you don't. You could imagine an alternative world where maybe we compared GPAs across different times, looked at high school students' morning and afternoon classes, and you looked at their grades. It would be easier to interpret differences there because we know what they mean. Because if the average difference were like half a letter grade, we'd know what that meant. The educational significance of the effect would be clear to most people. Most Americans anyway, who are familiar with GPA. But in in education, there's this nice, easy example of GPA, but in most other realms of experimentation in psychology, there isn't a familiar scale available where we could record the outcomes in a way that everybody would understand. So, to say nothing, of course, of instances in which an experimenter has to invent a scale or use a scale that is really specific to their area of research. So what we want to do then is convert our difference score to a more standard scale, a scale that we can use to assess the sizes of differences for any experimental manipulation. This might start to sound a little bit like z-scores to you, and in fact, effect sizes are in some ways equivalent to z-scores. So the effect size is just the standardized mean difference between the two groups. In other words, it's the mean of the experimental group minus the mean of the control group divided by the pooled standard deviation. Again, this is an example for an independent groups t-test for any situation in our class where you need an effect size in a more complicated analysis. You can usually click a button on your statistical software package and it will produce it for you. For example, in Dawson's time of day effects experiment, standard deviation is 3.3, the pooled standard deviation, so the effect size is 2.7 over 3.3, so it's 0.8. And so if you go back to the earlier table showing that rejection of the null hypothesis is easier as n increases, you see that the effect size is 0.6 for each of those. And so now we're kind of in a world where, all right, we've got one that's 0.8, one that's 0.6. What do those numbers mean? So Cohen, one of the originators of this concept, in 1969 defined effect sizes of 0.2 as small. Small meaning that you probably wouldn't be able to see them with the naked eye if we were talking about sort of a real world thing. So a nice example in the real world is the difference in the height of 15-year-old girls and the height of 16-year-old girls in the US. That's an effect size of about 0.2, so that's how small that is. An effect size of 0.5 is medium. Cohen called this large enough that it would be visible to the naked eye. This is like comparing heights of 14 and 18-year-old girls. And then an effect size of 8, Cohen called grossly perceptible and therefore large, and he equated it to the difference between 13 and 18-year-old girls in the US. So these are sort of standards that most people use when talking about effect size, and I'll talk a little bit more about what that means in just a second, but essentially, yeah, I'll hang on to that for now. Just to talk to you about who Cohen was for a minute, he was a statistician who was critical of null hypothesis significance testing decades ago. I highly recommend a paper from 1994 called "The Earth is Round, P is less than 0.05" that he published in American Psychologist. But his solution was to calculate effect size and to do power analyses. In 1994, he wrote a quote so well known from this Earth is Round paper that it's actually on his Wikipedia page, which I was surprised by. It's very short, but it has this quote that the fact that people misinterpret P leads us to need to move on from it, essentially, if I were to paraphrase what he said there. So he encouraged, in addition to these other two measures of effect size and power analyses, replication of research and meta-analysis, which are both things that effect size enhance and in a baser way can even enable. These are not perfect things, these effect sizes, primarily if we really hook tightly to terms like small, medium, and large. For one reason, for several reasons, one of which is that, as Glass et al. Argued in 81, the effectiveness of a particular intervention can only really be interpreted in relation to other interventions like it that seek to do the same thing. So to try to have a generalized way to compare all interventions is maybe not necessary. Glass et al. Also wrote that the practical importance of an effect depends entirely on its relative costs and benefits, and so to just have an effect size measure, a Cohen's d, doesn't tell you the whole story. So trying to move us away from what we're doing into this other realm of effect size instead of p is maybe not necessary. And some of that is solved by the fact that there is not just one way to calculate effect size anymore. There are lots of effect sizes out there for different designs, but they vary along the same principle. And there's this further issue that Glass et al. Don't mention, which is the fact that if we're just going to be interested in large effects or medium and large effects and no small effects, then we could end up with the same problem we have now, where work that is important and interesting and meaningful but doesn't get a large enough effect is hard to publish. The same as the current situation, where work that doesn't have low enough p-values is hard or impossible to publish. And so if we just move from using p badly to using Cohen's d badly, we aren't doing anything better for our science. So the goal of moving to Cohen's d, the goal of moving from p to effect size, is to change the way you think about your science. We're not looking for whether there's an effect. We're seeking to measure the size of an effect. If it's large, if it's small, we don't care. We just want to know what it is. We might have hypotheses that it's large and find out that it's small, or vice versa, and that's fine. All that work should be just as valuable as work that hypothesizes large effects and finds them. I think that's a good enough spot to end this video. Thanks for watching. See you in the next one.